Welcome back. So at the end of the last segment, we wrote out our ODE in its discretized form, and we've also introduced the Euler family, right? We've met the Euler family, so to speak. All right, what we want to do now is go ahead and apply it to our ODE, and the approach we are going to take is one of revisiting this discretized form of our ODE. Okay, so go back to our time discretized ODE. All right, we write it out as m v at n plus 1 plus k d at n plus 1 equals f at n plus 1, right? Where what we can say now is that we can invoke our Euler family as applied to our definition of v. Okay, so what this means is that we're saying here that d at n plus 1 equals d at n plus delta t v at n plus alpha, okay, where v at n plus alpha equals v n plus 1 multiplied by alpha plus 1 minus alpha times v at n. Okay, and in writing out these two equations, you can see that we have essentially applied this idea of the Euler family in there, right? Okay, all of this, of course, to complete our specification of even our time discretized form of the ODE. What we are saying is that, of course, with all this, we are given the initial condition, right? And that initial condition is d0. Okay, we know what we mean by d0, right? In the previous segment, we explicitly said what d0 is. All right. So now with, in general, you really see this idea of time stepping. The idea is that given things at dn, right, given quantities at given quantities dn and vn at tn, this is a scheme for going from n to n plus 1. Okay, and it uses the initial condition here. All right, now there are two sort of canonical approaches to solving this time discretized ODE, and we'll look at both of them in turn. The first is what is called the V method. Okay, somewhat unimaginatively. All right, here's the V method. In order to apply the V method, and actually to apply the other method as well, we go back and look at this form of the problem and look at these two equations and do the following. Okay, we first note that we can rewrite now dn plus 1 as dn plus delta t times vn plus alpha, but vn plus alpha is also written up for us here. So we'll write that as alpha vn plus 1 plus 1 minus alpha Vn. Okay? All right? So that's the first step. combining the two sort of equations that define the Euler family. Now, in the next step, what we're going to do is to rewrite this as, rewrite the right-hand side as dn plus 1 minus alpha delta t Vn plus alpha delta t Vn plus 1. Okay? Now, what we've done here, if you observe, is rewrite dn plus 1 in terms of quantities that depend only on quantities at n. Okay? So let's denote this as d tilde at n plus 1. Okay? Now, we are getting into the realm of what are called predictor-corrector methods. Okay? And the idea is that if we want to calculate dn plus 1, right, we have this formula for it, we predict this, right? We say that, well, this is our guess for what it is. Okay? And in general, that will not be correct, and we need to correct it with this term, which is the corrector. Okay? So, written differently, dn plus 1, actually not so differently, dn plus 1 is equal to the predictor, dn plus 1 tilde plus the corrector, alpha delta t Vn plus 1. Okay, so this is a predictor-corrector method. Okay, this V method that I'm talking about is one where what we do is return to our time discretized ODE, right, which is this one, mvn plus 1 plus k dn plus 1 equals f at n plus 1, right? We return to this equation and we try to rewrite it only in terms of V. Okay? And the way we can do that is to essentially use for dn plus 1 here this predictor-corrector form. Okay? So, substitute predictor corrector form for dn plus 1. All right. What that does then is leave us with m v at n plus 1 plus k dn plus 1 tilde plus alpha delta t k v at n plus 1. Okay? All of this equals f at n plus 1. All right? Now, I said that the reason we call this the V method is because we are going to try and rewrite our discretized ODE entirely in terms of V, right? Entirely in terms of Vn plus 1. So that is indeed what we do. Okay? So we get here, this implies m plus alpha delta t k Vn plus 1 equals f n plus 1 minus k d tilde at n plus 1. Okay? We solve this equation for v, for Vn plus 1, and we now have the corrector, right? Because then we can add Vn plus 1 from here up there, and we get the corrector step. All right? Right, so basically we solve it's this inverse acting on Fn plus 1 minus k d tilde n plus 1. Okay? Right. Now, I'm going to make a couple of remarks. Okay? And those remarks are the following. Right? Now, the first remark is that if instead of m, we use the lumped mass, okay? And furthermore, we use alpha equals 0. Okay, this would be forward Euler. Okay? If we have this particular combination, then what we see is that for V n plus 1, which is lumped mass inverse Fn plus 1 minus k d tilde n plus 1, okay, because the lumped mass is a diagonal matrix, its inverse is trivial, right? So as a result, we don't really solve equations here, right? We don't have to solve a linear system of equations by somehow effectively generating that inverse. Okay, so this is what we call an explicit method. Okay. In contrast, we have if alpha is not equal to 0, okay, right, then we have in that case, even if our mass is lumped, we still have equations to solve. Okay, so this is now an implicit method. All right. Okay, so these are two remarks to make, and what we will do is move on and proceed directly to the other canonical solution method, which is the D method. Okay. In the D method, once again, we could look at our predictor-corrector form. But now we sort of turn this around to eliminate V from our discretized ODE. All right, what that implies then is we write here we get Vn plus 1 equals d n plus 1 minus d n plus 1 tilde, okay, and divided by alpha delta t, okay. This of course holds only if alpha is not equal to 0. Okay, all right. And in this case, we get V from here, and then we substitute it back into our discretized form of the ODE. Okay, and okay, so when we substitute in our discretized form of the ODE, m for Vn plus 1, we had dn plus 1 minus dn plus 1 tilde divided by alpha delta t, right? That is our approximation for Vn plus 1. Well, that's our expression for Vn plus 1 using the Euler family. And here we have k d n plus 1 equals f at n plus 1. And this again we reorganize by simply multiplying through by alpha delta t. Okay, so we get m plus alpha delta t k d at n plus 1 equals alpha delta t f at n plus 1 minus m d tilde at n plus 1. Okay. Now in this form, of course, you realize that when you get to the final form, it doesn't matter if alpha is equal to 0. Therefore, this works even though I wrote that in defining Vn plus 1, right? Even though I wrote that alpha is set equal to, alpha cannot be equal to 0, right? We still get back our, we are still able to actually solve the equation and move on. Okay, so this would be the V form, and now what we get here is d n plus 1 equals m plus alpha delta t k d n plus 1, sorry, inverse here times alpha delta t f n plus 1 minus m d tilde n plus 1. Okay. For this sort of method, if we use a lumped mass, right? If we use a lumped mass here, what is seen is that we require less effort to set up the right-hand side. Okay? All right, if we use the lumped mass here, there are fewer operations. Not less, let me make that fewer operations. Fewer operations to form the right-hand side. Okay, but the actual equation solving effort in the two methods, the V method and the D method, is the same. All right, so here we have it. Our these are the two methods by which we can set up the solution of this problem. You observe that you're still solving exactly the same set of equations, so the methods are really equivalent. It's just a matter of which variable you attempt to eliminate first. Okay? Right. So what we can begin to do now is to proceed to the actual solution, and well, sorry, we've already looked at the solution techniques. What we can do now is to set ourselves up to carry out an analysis of these methods. Okay, and that may perhaps be done best in a separate segment. So when we return, we'll take up the analysis.